Hi, I'm Jinhwa, coming to you from beautiful Seoul. In this video, we will review an ICLR paper in this year from NAVER AI Lab. That is AdamP, slowing down the slowdown for momentum optimizers, renowned for the superior performance across many tasks. Basically, it's a simple correction to momentum-based optimizers, that is SGD and AdamP with momentums. This is not limited to AdamP. It claims a general applicability to momentum-based and gradient-based optimizers. They evaluate on many benchmarks, achieving better performance than the baselines. First, let's see what normalization layers are. We define the normalization layer like this one. You can see that this is a simple version of batch normalization. Notice that L2 normalization also can be expressed in this form if min is 0. Some interesting property of normalization is scale invariance, where C is a scalar which scales the input, but it does not change the output due to normalization effect. Even backward operation does not change. If you really wanted to know the port invariance, please see this. And backward invariance can be shown easily using the quotient rules for differentiation. Another interesting property is orthogonality between the weight W and its gradient. The proof is simple to show. Then we will show that effective step size by gradient descent in the presence of normalization layer. This is a vanilla gradient descent updating rule. Assuming that the norm of weight is unchanging at a certain point, the effective step size is discounted by the norm of the weight. Right here, actually, the norm of weight is monotonically increasing. Using the previous orthogonality and Pythagoras' theorem, we can easily get this. The norm of scale invariant parameter is monotonically increasing, and consequently, the effective step size is decreasing. By the way, surprisingly, the gradient descends with momentum more rapidly, increasing the norm. Using the momentum, the norm growth is more rapidly increasing by the discounted accumulating term. The proof in the appendix uses mathematical induction. However, we can prove by deductive reasoning. We just use the previous definition and the orthogonality, which makes the Lemma 2.2. Corollary 2.3 involves some strong assumptions. However, it gives us an interesting aspect, the norm growth comparison between vanilla GD and GD with momentum. Here, it assumes that each gradient of vanilla GD and the velocity of momentum GD is the same for mathematical convenience. Here, we show the proof. From the Lemma 2.1 and 2.2, we obtain A6 and A7. Then, we can see that the corollary turned into a simple form, A8. The spoiler is the right-hand side of A8 is the upper bound of geometric sum of beta, starting with beta, and AK, the norm of gradient, is diminishing as t goes to infinite. To prove formally, we bring about A9 and A10, the condition of AK and the residual of geometric sum. The first step is to break down the range of t with a large T and T prime. In the inside of parentheses, it's just a rewritten form. Using the concept of residual, we rewrite that. Notice that all1 is actually negative, but it doesn't care much. The residual R2 has a wrong bound. I believe this is a simple typo, and the authors confirmed this by personal communication with me. R3 comes from the previous A9. A16 rearrange the equation. Then, using the triangular inequality and the norm bounds, we give the inequalities. With a suitable constant m, the proof is completed. So, the norm growth of GD with momentum may be the issue, which potentially leads to the underperformance of optimizers. The paper proposes a nice remedy using vector projection. A perpendicular vector is WT, and the green hyperplane shows a subspace of the gradient. The direction of p t-1 can have arbitrary direction compared to the gradient. pt contributes to increases the norm of WT more rapidly compared with the vanilla GD update only with the gradient. The proposed method is to project PT onto the green hyperplane where the gradient may reside. It prevents extra norm growth by the momentum. This figure illustrates how to calculate the projection. The unit vector with the direction of WT is used to project PT by dot product, and the difference between PT and the projected vector, blue, indicate the projected vector of PT onto the hyperplane. Algorithm 1 and 2 shows where the projection is applied. Notice that the weights subjected to normalization are the targets for the projection. Some computational cost is unfortunately unavoidable. This paper shows a lot of experimental evaluation. The first one is a toy example of Rosenbrock. Additionally, the lower low shows the change of the weight norm over the iterations. The experiments includes the image classification and retrieval, music tagging, object detection, audio classification, and language modeling. Lastly, the limitations. This update of projection only makes sense to the weights subject to the normalization layers. The projection cost is not small. Some experiments took 8% more training times with the same iterations. However, please see that table H7 in appendix that shows its efficiency with a control experiment. With the same training time budget, it outperformed AdamP. I think theoretical analysis on the AdamP is a bit unsatisfactory, but I have to say that it is based on the plausible assumptions on the increasing weight norm and proposed a good remedy for it, confirming with the strong benchmarks. It's all. Thanks for watching this video. See you again.